This lecture reinforces material from Section 1.3 and the Working It Out Units and Scientific Notation block in the textbook. The central learning goal of this lecture is how to record experimental data. Specifically, this lecture explains how to express measurements numerically, perform unit conversion, and propagate errors. For the online astronomy labs, you won't have to concern yourself too much about recording errors properly. The emphasis here is on concepts and relative quantities and not doing math. But this is a science course, so it would be wrong to not include some statements about how data are recorded. Here are some examples of measured quantities. 20 yards plus or minus 2 inches, 3.45 million kilometers plus or minus half a kilometer, 29 seconds plus or minus 35 nanoseconds. In the lecture regarding Step 4 of the Learning Astronomy by Doing Astronomy, or LADA, Activity 1, the source of uncertainty or error in measurement was discussed. The accuracy, that is the correctness, and the precision, that is the number of significant figures, of a measurement are always limited by the degree of refinement of the equipment, by the skill of the person using the equipment, and by the basic physics in the experiment. Recorded numbers should neither be overspecified nor underspecified. That lecture explains how systematic and random errors combine with limitations of the instruments to give a value of uncertainty. When a scientific number is recorded, include both a numeric measurement and an uncertainty or error on that measurement, and of course the units. For many of the labs, though, where you're inputting numeric data into Blackboard for being corrected and submitted, you don't express the error. Only express error when it's explicitly asked for. Most of our measurements are using the metric system. The metric system is convenient because it uses base 10. A gram is about the mass of a pen cap, or a cubic centimeter water, or a Smartie candy, whereas a kilogram is about 7 apples. A liter of air is about a gram, and a liter of water is about a kilogram. A meter is about waist high on a typical adult, and a kilometer is a little over half a mile. 1 U.S. nickel has 5 grams of mass, and 20 U.S. nickels weighs about 1 Newton, and an apple weighs about 1 Newton. That's convenient, Newton's apple. A unit of measurement is a definite magnitude of a quantity defined by convention that is used as a standard for measurement of that same quantity. Any other value of that quantity can be expressed as a simple multiple of the unit of measurement. There are 7 base quantities: length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. By convention, there are certain symbols that are used for these base quantities in formulas and in dimensional analysis. The SI units are also given in the table here. Other symbols may be used in formulas, so you have to watch how the formula is defined. One of the most confusing college lectures I attended was in electricity and magnetism, where the Greek letter rho was used as a radial distance, as a charge density, and as a resistance, all on the whiteboard, all at the same time. Other quantities such as area, pressure, and electrical resistance are derived from these base quantities. For example, speed is distance traveled divided by time of travel. The conventional symbolic representation of the dimension of a derived quantity is the product of powers of the dimensions of the base quantities according to the definition of the derived quantity. The exponents are positive, negative, or 0. The symbol may be omitted if its exponent is 0. The table shows the various quantities such as speed or power that are derived from these 7 base quantities. Two numbers can be added or subtracted if they have the same dimension. We can't add 3 miles in 10 seconds. That's nonsensical. Any physically meaningful equation, and likewise any inequality, will have the same dimensions on the left and right sides, a property known as dimensional homogeneity. Looking for dimensional homogeneity is an important skill used in solving physics problems. We can, however, add 3 miles and 1.6 kilometers, since both terms are lengths and thus the terms have dimensional homogeneity, but they need to be first expressed in the same units, to sum their values to create a single term. 1.6 kilometers is approximately 1 mile, so 3 miles plus 1.6 kilometers is 3 miles plus 1 mile, which is 4 miles. Unit factor analysis, also called factor label method or the unit factor method, is a technique based on the identity operation. That is, any number or expression can be multiplied by 1 without changing its value. It is a very useful technique for many unit conversion problems. We form unit factors from relations that equate to units. For example, we know that 1 inch equals 2.54 centimeters. There are 2 unit factors that can be created. 1 equals 1 inch divided by 2.54 centimeters, and 1 equals 2.54 centimeters divided by 1 inch. Any number can be multiplied by 1 to get the same number, but we need to keep track of the units when we multiply by the unit factor. The next few slides give some examples of unit factor analysis. In today's internet resources, unit factor analysis is sometimes called dimensional analysis. This is disappointing. At best, unit factor analysis is a small subset of dimensional analysis. In engineering and science, dimensional analysis identifies the relationships between different physical quantities on the basis of their fundamental dimensions. In 1822, Joseph Fourier introduced the concept of physical dimension and dimensional analysis. The MIT YouTube video Dimensional Analysis is about 20 minutes and explains how to use dimensional analysis to design a parachute for landing on a rover on Mars. This video is included after this lecture. If you're interested in understanding what dimensional analysis is all about, please watch that video. You will not be expected to do dimensional analysis in this course, but it is a very powerful tool. Let's start with unit factor analysis of time. We know that 1 day is 24 hours. We can form from this 2 unit factors. 1 day divided by 24 hours is 1, and 24 hours divided by 1 is 1 day. Likewise, 1 hour divided by 60 minutes is a unit factor, as is 1 minute divided by 60 seconds. A unit factor can be found from the product of 2 unit factors, since 1 times 1 is 1. Here the product chain of 2 unit factors yields a unit factor of 1 hour per 3,600 seconds. Notice that the units are treated as if they were algebraic quantities being canceled when they appear in both the numerator and the denominator. Here are some examples. First, find the number of minutes in a day. We take our quantity of 1 day and multiply it by 1, that unit factor of 24 hours per day, and then multiply it by 1 again, that unit factor of 60 minutes per hour. Cancel the units of hours and days as if they were algebraic quantities in the numerator and denominator. The result is that there are 1,440 minutes in a day. Now, how many seconds are there in a year? Do the same thing, but include 2 more unit factors so that we can convert from years to days, then from days to hours, then from hours to minutes, and finally from minutes to seconds. There are 31,557,600 seconds in a year. What is the age of the universe in seconds? The age of the universe is about 13.8 billion years. We can just multiply by the unit factor found in the last problem to get that the universe is about 4 times 10 to the 17 seconds old. Those equalities of length units can be used to form unit factors as well. 1 kilometer is 1,000 meters. 1 mile is 1,609.24 meters. The Earth radius is about 6,371 kilometers. Many distances to objects near Earth and the sizes of the outer planets in the solar system are expressed in Earth radius values. We'll see how using proportional reasoning and this natural unit of Earth radius makes some problem solving easier. The astronomical unit is about 1.5 times 10 to the 8 kilometers. Distances to planets in the solar system are often expressed in the astronomical unit. Light years and parsecs are also distance units, as we saw in the first learning module. How far is 6.6 Earth radii in miles? We can find this by converting the Earth radius to kilometers, kilometers to meters, and then meters to miles. cancel the units of Earth radii, cancel the units of kilometers, cancel the units of miles. It's over 26,000 miles from the center of the Earth. This is roughly to the distance of geosynchronous orbit, where many of our telecommunication satellites live. What about 60 Earth radii in miles? That is approximately 238,000 miles, and roughly the distance to the moon. Most people get excited when their odometer in their car cycles to 100,000 or 200,000 miles. Astronomers get excited at the distance to the moon of 238,900 miles. Unit factor analysis works for velocities as well. We can inform the velocity unit factors by multiplying by different conversion factors of time and conversion factors for length. So here we're seeing how 20 meters per second can be converted to miles per hour by chaining our factor of 1 mile per 1609.24 meters, and then times basically the 3600 seconds per hour. For unit factor analysis of density, we're usually just going to be using the conversion that 1 gram per cubic centimeter is 1,000 kilograms per cubic meter. Some interesting densities to know are that the Earth's crust is about 2.9 grams per cubic centimeter, the mantle 3.3 grams per cubic centimeter, but the core is much more dense, is 13.1 grams per centimeter cubed. So this is showing the differentiation of density, and we'll talk more about that in Chapter 5 and Chapter 6. Temperatures can't be converted using unit factor analysis. Unit factor analysis does not work for scales that have different 0 points. For temperatures, you need to convert using formulas. When numbers that have uncertainties are combined algebraically, that leaves the question of what the resulting uncertainty is. The process of determining the resulting uncertainty is called the propagation of errors. When you multiply a number by a constant, then the uncertainty is just the product of the absolute value of the constant and the uncertainty. In this example, we measured the radius of a circle to be 2 meters plus or minus 3 centimeters. We want to know the circumference. The circumference we find from a formula. Circumference is 2 pi r. So we'll multiply everything by 2 pi. So the circumference is 4 meters plus or minus 19 centimeters. When you add or subtract numbers, the uncertainty of sum or difference is the square root of the sum of the squares of the individual uncertainties. For example, if you measure a length of a rectangle to be 2 meters plus or minus 8 centimeters and the width of that rectangle to be 1 meter plus or minus 3 centimeters, then the perimeter of the rectangle is 6 meters plus or minus 17 centimeters. When you multiply or divide numbers, the uncertainty of the product or ratio is the product of the resulting value and the square root of the sum of the squares of the ratios of the individual factor components to their respective values. For that rectangle of 2 meters plus or minus 8 centimeters and width of 1 meter plus or minus 3 centimeters, the area is obviously 2 square meters. But then to find the uncertainty, it's plus or minus 2 times the square root of 8 halves squared plus 3 squared, which is 5. So it's 2 meters squared plus or minus 10 square centimeters. In summary, astronomers use math to find patterns. Recording a measured value requires specifying the value, the uncertainty of the value, and the units. Unit factor analysis is a way to convert from one unit to another by exploiting the identity operation. That is, that multiplying any number by 1 gives you the same number. Uncertainty values of derived quantities are found by propagating errors.